in Paris at the University of Pierre and Marie Curie, and he's talking about the asymptotic analysis of some selection mutation models.
Okay, thank you, Lisa Maria. It's rare that I get introduced with such a good pronunciation of my name, so thank you. And of course, first of all, thanks. I want to thank the organizers for letting me talk here. So as it is indeed written here, I'm going to talk about the asymptotic analysis of some selection mutation models, and essentially this will be some kind of reaction-diffusion equations. And all this is a work with either one of these persons here. So Jean Clérambault and Emmanuel Trella, who are my PhD advisors at University Paris 6. Tommaso Lorenzi from the University of St. Andrews, and Alexander Lotz from KAUST and UPMC as well. So let me start by introducing the types of models that we'll be considering, and they actually very much look like the very simple logistic ODE. So you have, and the rest of the talk will have individuals that proliferate and die, and so here for the logistic ODE, R will always denote certain reaction rate, which is proliferation minus death. But they also have, this is a logistic assumption, an added death rate, which is assumed to be proportional to the number of individuals n. And the underlying question of the entire talk actually is, what happens if these individuals are allowed to have different proliferation and death rates depending on a certain continuous variable which will be denoted by x? So you can think of x up until at least now as a space variable, and you will just say that depending on where they are in space, the individuals have more food or less food, there is more competition, and you want to model this. And this means for the for the term, the logistic term, this is changed as follows. Now you have a certain kernel k of xy, which tells you the strength of the competition between for cells at position x coming from cells at I'm saying cells but individuals at position y. And I will assume that k is non-negative, which means that essentially there is a competition, but you could think of k as being negative as well for mutualistic interactions. Okay, so that means the models now looks like this. You have a certain function r of x, which is again the reaction rate, and you have a non-local term with this kernel. And at this stage, the equation is purely integral differential. And you start from a non-negative initial condition on a certain regular domain of RD, but it could be the whole RD. And I will also allow in the rest of the talk this additional term for, if x is a space variable, you have the possibility for individuals to move randomly in space, so you have a Laplacian. And I put a beta in front because I also want to consider the case of beta being equal to 0. So if the domain is bounded, I have Neumann boundary conditions. And let me just mention that you have existence and uniqueness of a classical solution for this equation, at least if beta is positive. Yeah. So again, I want to talk about asymptotic analysis of this. Yeah.
Is that true for any k?
Yeah. You have a regular k, so that's what I meant by regular, reasonable regularity hypothesis, like an infinity kernel, say. Okay, so in terms of asymptotic analysis, let me explain the kind of results that we already have on these types of equations and why it's not necessarily easy to understand the behavior, the asymptotic behavior. So the first thing is the first case that I want to consider is indeed when x is the space variable. So in this case, let me take this equation. So recall the previous equation. So I'm taking r of x to be equal to 1 for simplicity. So all the individuals have the same, let's say, kind of the same proliferation and death rate. And the competition term comes from a certain convolution. And in the case of a space variable, you will say that the individuals at position x will essentially interact with the individuals which are close to them. So you will expect that the function phi here is localized near 0. And you have a normalizing condition. See, the integral of phi is 1. And you see that in the limiting case where you say, okay, individuals are actually interacting only with the other people at the same location, then this would boil down to saying that phi is just a delta function, in which case you recover what is called the Fisher KPP equation. So it's just a parabolic equation with the logistic ODE here and a diffusion. So this is very classical in population dynamics. And this equation with the kernel phi is called the non-local Fisher KPP equation. Okay. And it is known that for this, for the local Fisher KPP equation, 1 is globally asymptotically stable. So what do we know about the asymptotic analysis of these types of equations and other related questions? So the first result is, of course, you have, for positive beta, the function is bounded in L infinity, but I want to emphasize, and you will see why it's important later, that the bound is uniform in beta. That means even if individuals move really fast in space or very slow, you can have a uniform bound which does not depend on this, let's say, speed of moving in space. Okay, this is proved at least in 1D. But okay, now people look at this equation and they typically wonder whether the results that are true for the local equation remain true for the non-local equation. And the important result is that 1, which is clearly a stationary solution of this equation, is globally, so you have another one which is 0, and 1 is actually the unique non-trivial stationary solution, so apart from 0, when phi is localized enough. So that means, starting from this equation, when phi is close enough to the delta function, so again, it's localized enough, near 0, then 1 is the unique stationary solution apart from 0. And actually, the condition is a condition of the Fourier transform.
Sorry, is conditions related to the value of beta or is it dependent of beta?
It's independent of beta. Yeah. It's just if you take the Fourier transform of this, you just compute, and this is what comes out. Okay. And also you have, which has been introduced by Nicolas Bouchelet, the existence of traveling waves. So what it means is essentially if you start from an initial condition which is compactly supported in space, then the 1 will take over the whole population, the state y, with a certain speed. Okay. So that's the type of result we have of these equations. Now let me consider the case where x is more a phenotype variable. So the classical example that people give for these equations is to say, for example, you have let's say giraffes, and they have different lengths of necks, and you want to understand why an optimal neck exists, let's say, because you want the giraffes to be able to grab fruits in the trees, right? So now there is no reason why, let's say, giraffes of a certain neck length will interact only with those with the length which is close. So that means, in terms of the kernel k, you could imagine the simplest case would be even taking k to be constant. So in the case when k is constant, then the equation becomes the following. So you still have this r of x, but now the non-local term is simply d times rho of t, which will be, in the rest of the talk, the total number of individuals. So this is completely different. And in terms of the behavior of the equation, it's very different as well. So a few things. So if indeed k, let's say you can think of k as being constant for simplicity. So if you want to look at what's going on asymptotically, what happens is you look at the first eigenvalue of this operator, and if this eigenvalue is non-negative, then the population will become extinct. However, when this first eigenvalue is negative, then you will converge to a multiple of the first eigenfunction of the operator. Okay. So that's what is known, let's say, in terms of asymptotic behavior. But again, you have to take a very specific kernel. And also what is very important is that you have an infinity bounds again for a given beta positive, but if beta tends to 0, so if, I should have mentioned now, what does that mean to have this Laplacian term? Now, this Laplacian term models the mutations inside the population. So the individuals give birth to new individuals who have slightly different traits, have slightly different phenotype, and that explains this term. So you could say, well, that's really not satisfactory. What does it mean for beta to have bounds that blow up? So what it means is that when beta is small, and actually, let's say in the limiting case of beta being equal to 0, so no mutations, then asymptotically you can have solutions that tend to Dirac masses. And this is actually a nice thing, because in terms of modeling, what you want to model is the selection of certain theta phenotypes. So a certain neck length for the giraffes, okay? So, but what I want to emphasize here is you see you have really different behaviors depending on the kernel, and the question is it possible to find, an approach which is, let's say, systematic and does not depend on the kernel? Well, that does not will depend on the kernel, but lets you treat both cases, the phenotype and the space case. Okay, let me start also by being more specific about this equation. So this is a previous equation in the phenotype case. So k is non-localized and is 0. It's just, let's say, a constant. In more generally, it would be a function of x here. And recall that rho is the total number of individuals. Here, the phenotype is between 0 and 1 for simplicity. So what do we know about this equation? So what I'm going to state now is still known. We know that the first result is that the total number of individuals converges to a certain value which can be computed explicitly. So rho converges, and you can compute the value explicitly. And the second thing is, so this is a certain plot of rho, so there is a plateau. And now in terms of the density itself, if you start from some Gaussian, here I have chosen the parameters such that 0, the phenotype 0, has a selective advantage. So starting from an initial condition, you see that you have convergence towards a Dirac mass at 0. Okay, so and the result is the following. U concentrates on a certain set of phenotypes that you can compute explicitly. And if this set is reduced to a singleton, then you have convergence to a Dirac mass in the sense of measures. Of course, you could ask what happens if there are two phenotypes in this set. Now it's a complicated question, but I don't have time to talk about this, but just mention it's interesting. Okay, so again, my goal is to find, if possible, an approach which could be applied to both cases, and some condition on the kernel under which you can say, well, it converges to this or to that. And also, if I just take this simple equation, it's quite simple actually, this integral differential equation, the first statement, which is that rho converges, the technique to prove it fails completely for systems. So you also want to have a technique which is suitable for the study of systems. Okay. And this will be done, I will present some Lyapunov, a certain type of Lyapunov functional that allows to treat different cases for these equations. So let me explain the idea of the equation, at least the way I see it, is let's go back to the ODEs and let's go back to a simple standard Lotka-Volterra system. So you have n interacted populations, so n species, let's say, and the species I has a certain proliferation rate, reaction rate Ri, and they have an interaction competition term, let's say, with the others, which is given by this interaction matrix of coefficients Aij. And let's imagine with your ODE, you have a certain stationary state called a persistent stationary state, because you have all the species which are present at asymptotically, or you expect them to be present asymptotically, and you wonder whether this state is stable, say, if possible, globally asymptotically. And the Lyapunov function that has been introduced in the 70s by Go is the following. So maybe let's forget about the sum and the lambda j for the moment. So the basic function is this one. So it's z minus 1 minus log of z, which has the nice property to be a non-negative function. And now you sum these functions, you weight them with some lambda j's that you aim at choosing nicely. And if you compute the derivative of v along trajectories, you find a quadratic term, and the matrix involved is A transpose D plus dA. So A is a matrix of coefficients Aij, and D is the diagonal matrix where you put the lambda i's on the diagonal. So in other words, you see here, if you want to have a Lyapunov function, so if you wanted to decrease along trajectories, you are led to assume that you can find the lambda i's such that A transpose D plus dA is positive definite. It's not clear for which matrices this is possible, but there is a big class of matrices, actually, where you can find such a D. So in this case, the whole Lyapunov theory for ODEs just applies nicely, and that means you converge to this stationary state. And this gives a nice idea for a possible Lyapunov function for the case we are considering here. Namely, let me start with the equation we had before, so in full generality, but I don't have diffusion. So for a long time now, I will just deal with the cases of no diffusion, no mutations, depending on what we consider. And again, we have a stationary solution, and we're wondering whether there is some stability. And it's very natural to consider the Lyapunov function, which is exactly the continuous version of that Lyapunov function. So now this is exactly the same, and you have a weight function m that we want to tune nicely. Okay. So the first thing is you're now in finite dimension, so it's not clear whether this term u infinity log of u infinity is well defined, especially because I don't have diffusion here, so you lose regularity. But if it is defined, if everything is fine here, then v is a non-negative function, and you want to do the same computation that you did for the OD. So you go ahead, you compute, and along trajectories, you find that the derivative is given by this term, which is also quadratic, and now the equivalent of the matrix we had before, A transpose D plus dA, is this term, which is symmetrized here. And it's quite natural at this stage. So this is a theorem by Jabin and Raoul. I mean, it's less general in the paper, but it's the idea of the Lyapunov function is from them. So if you can find a weight function such that this kernel is positive definite, then the stationary state is globally asymptotically stable. But here you have to specify in which space it is stable, and it's not very important, but it is stable in the sense of this norm given by the kernel. Okay. Problem is, recall that in the phenotype case, so this works nicely if you expect that everything will be well defined, let's say. But in the phenotype case, when you have a stationary solution, recall that we expect it to have asymptotically a Dirac mass. So this doesn't even make sense. So that means when you consider the Lyapunov function, you are not allowed to put this term, which at first glance is not a problem, because u infinity log of u infinity does not depend on t. So in terms of computing the derivative of v, everything is the same. But you lose the fact that v is non-negative, which is really crucial in using Lyapunov function, because you use that v decreases along trajectories and non-negative, so you will say v converges to a certain value, so you lose this. And so it's actually huge in terms of technicalities. Okay, so let's get rid of that term anyway and see what happens. And so I will explain now how we can deal with integral differential systems with these types of Lyapunov functional. So I have this equation. So again, I'm really in the phenotype case. So I expect asymptotically to have a Dirac mass. Here, k of xy, the kernel is simply d of x. I have a stationary state. I have the total mass, asymptotic total mass, so the mass of the stationary state. And I'm going to consider the previous Lyapunov function. So here you have no longer the u infinity log of u infinity, And believe me, the right way to put is 1 over d of x. So, and indeed, when you compute the derivative of v, and I'll come to the systems afterwards, you'll see that this goes nicely to systems. It's very nice because somehow you have 2 terms, one which is linked to the convergence of rho to rho infinity, and the other one which is linked to the concentration phenomenon of going to a Dirac mass to certain phenotypes. And these 2 terms have a sign. So they are both, so again, v decreases along trajectories. But at this stage, it's not clear how you're going to prove that it converges to the stationary state because you have lost the sign of v. But still, what you can say is you can try to estimate v from below, and this is the kind of estimate that you can have. So it decreases, okay, v is not non-negative, but still. And also there is some kind of magical function. So if you take convergence and concentration and you mix them in the right way, convergence plus 2 times concentration is a non-decreasing function. So these 2 estimates somehow are enough to tell you that v, so the derivative of v tends to 0, and you have actually an estimate of how fast it converges to 0. And if you look back, you look at this equality, that means that you have convergence of rho towards rho infinity at this speed, and concentration also at that speed. So it's very nice because you have also something quantitative. Okay, and well, maybe I'll be a bit quicker on this. This goes well also when you look at systems. So now it was actually why I started looking at these equations, because I have this system of two equations representing cancer and healthy cells under chemotherapy. The phenotype was the resistance to the drugs, and we wanted to understand what was going on, and we needed to find Lyapunov functionals to do something. So here, in full generality, I'm in dimension n. I have n species. All of them are structured by a certain phenotype. And you have a stationary state. You have a Lyapunov function. Now, the Lyapunov function is a big mix of the Lyapunov function that I've designed before and the Lyapunov function for the Lotka-Volter ODEs. So you have to put new weights here, lambda j. You compute everything. And again, you have a term which is linked to convergence, one that is linked to which is linked to concentration. And doing the same kind of tricks, you end up with the same conclusion, but you have a stronger hypothesis on the matrix A. Okay, so it's just same types of computations. Okay, now you could ask, okay, well, that allowed me to treat, let's say, the phenotype case when there are no mutations. Now, what about adding diffusion? So, at first glance, it looks better, because recall that the problem was this term u infinity log of u infinity. But when you add diffusion, then everything is regularized, so these terms make sense, and there is no problem looking at this functional right away. The problem is when you compute the derivative, formally you have a new term which comes from the diffusion term. And there is no reason why this should have a sign, and if it does not have a sign, whether it's going to be balanced by this term. And the thing is, recall that we have a degree of freedom, which is the weight that we're going to choose. And the fact is, if you want the diffusion term to have a sign, to be non-positive, you need to take a very specific m of x, and actually you need to take exactly the stationary solution. So where does this idea come from? It comes from the entropies for parabolic equations. So for those who know, when you have a parabolic equation and you want to look at, to build entropies, what you do is you look at the stationary state, you look at the dual equation, and you take a convex function, evaluate at the quotient, and here, this is exactly what we have with the convex function h, which is given by this. So the dual equation is the equation itself, because you just have a Laplacian. So in the end, this is the right way to put if you want to have a sign from the diffusion term. And indeed, when you compute the derivative with this term, you have a new term here, which is non-positive. So again, it looks nice, because then now you say, OK, this is non-positive, so I just have to ask to this term to be non-positive as well. So let's do this. Let's assume that the kernel is such that this is positive definite. Problem is you don't know what U infinity is. So this is completely an implicit hypothesis. It's not an hypothesis made on the data, or you have to explicit what it means on the data. And so far, the rest, I'm still looking for cases where I can really make this implicit hypothesis explicit. And there is one nice case where it is very explicit. And you could say, well, that's stupid, but still, when U infinity is equal to 1, then this is a condition on the kernel itself. If U infinity is equal to 1, then asking this is asking that k of xy, once it is symmetrized, is positively finite. And actually, in terms of the application, it's nice because a case where U infinity is equal to 1 is for the non-local Fisher KPP equation. I talked about this equation at the beginning. This equation is looked a lot in the math bio community because, again, it's a generalization of the classical Fisher KPP equation. And it's an open question to know whether 1 is still a stable steady state once you have a kernel here. And with this Lyapunov function, you can actually prove that if k is positively finite, so here is an is, then 1 is globally asymptotically stable for this equation. And maybe in a few words, what is the idea of the proof? Because in finite dimension, for ODEs, you have certain techniques for Lyapunov function. Essentially, you ask the function to be decreasing along trajectories, to be non-negative, to be proper, to go at infinity, to infinity at infinity, so certain simple things. And the fact that it is proper, it gives you compactness in finite dimension. And in finite dimension, compactness is much harder to obtain. So let me just give a sketch of the proof. First, you need compactness of trajectories. Here it's easy because you have a trajectory starting from an initial condition which is non-zero. And it's going to be a very smooth function, so it's relatively compact, say, in this space. And because v is decreasing along trajectories, it's supposed to converge to a certain limit. And the second step, so it's actually I'm just doing again the LaSalle invariance principle somehow, but I have to tune things a little bit depending on the equation I have. And the nice idea of LaSalle is to say, now I'm going to let another trajectory start from the limits that I had at the end of the first trajectory, and I'm going to prove that the Lyapunov function is remaining constant during this second travel, let's say. And when you use this, you say that the time derivative has to vanish, and this tells you that actually the point that you had reached at the end of the first trajectory has to be 1. So this is a quick sketch of proof. And I think that ends my talk. These are some references linked to what I've introduced. Essentially, the two papers that are linked to what I've said are these two ones, and I also refer to Jabin and Raoul for a nice, let's say, study also of these types of Lyapunov functions. Thank you.